Good morning, students. We are going to discuss Module 2, that is Corrosion Science and Analytical Techniques. Under Module 2, we are going to discuss types of corrosion. So we have three types of corrosion: differential metal corrosion, differential aeration corrosion, and stress corrosion. So one by one, we will discuss about them. We will go into details and we will connect them to the real life examples. So let's start with differential metal corrosion, which is also termed as galvanic corrosion. So as you see here, we have taken the real life examples where two dissimilar metals are in contact with each other. Here you can see copper and steel, copper and steel, copper and iron, magnesium and iron. And you can see here, when two dissimilar metals are in contact with each other, the metal which is acting as anode is undergoing corrosion. So here you can see clearly how iron is corroding. It's so faster, and the amount of corrosion is increasing towards anode as we are moving further away from the cathode junction. Here you can see. So, and here magnesium is getting corroded when it is in contact with iron. So what can we infer here is that when two dissimilar metals are in contact with each other, a galvanic cell is set up and the current flows. The metal which is acting as anode will undergo corrosion, while the metal which is acting as cathode will remain unaffected. Now, how to understand what is cathode and what is anode? So if you go through electrochemical series, the metal with higher negative reduction potential will act as anode always, and the metal with lower negative reduction potential will work as cathode. And here you can see easily, since if we are taking the bimetallic couple of iron and copper, so in this case, iron will work as anode, copper will work as cathode. If we take the bimetallic couple of iron and zinc, in that case, iron will work as cathode, zinc will work as anode. So if we see the standard reduction potential difference of these two bimetallic couples separately, you will see that the difference in standard reduction potential in the first case is more as compared to the standard reduction potential difference in the second case. So in the first case, iron will undergo corrosion, while in the second case, zinc will undergo corrosion. How to know that? It is clearly evident from this standard reduction potential. So when we have iron with copper, iron will undergo oxidation reaction, iron will form Fe2 plus, and electrons will be released, which will pass on to cathode. Similarly, when iron is in contact with zinc, zinc will work as anode, electrons will be released due to oxidation reaction, and electrons will be transferred to cathode. At cathode, oxygen with moisture and with these electrons, they will form together hydroxide ions, and hydroxide ions will further react with the anode metal to form rust at the end. So always the metal which is acting as cathode will remain unaffected, while the metal which is acting as anode will undergo corrosion, which is clearly evident from these pipes. Now our next topic is differential aeration corrosion. So in differential aeration corrosion, as you see, a metal rod is immersed half in water and it is exposed, and some part of it is exposed to the atmospheric air. So the part which is exposed to the atmospheric air will work as cathode because, as we have studied earlier, reactions which are related to oxygen, they are occurring at cathode. So more oxygenated area will work as cathode, while the less oxygenated area will work as anode. Because the amount of oxygen dissolved in water is lesser as compared to the amount of oxygen which is present in the atmospheric air. So in this case, the upper part will work as cathode, while the lower part will work as anode. And as we have studied earlier, the anodic area will undergo corrosion, while the cathodic area will remain unaffected. So for today, that's it. We will discuss further the pitting corrosion and stress corrosion in the next class. Thank you.